This is a walkthrough of Problem 1 on Practice Exam 2 of Module 10 in the book Problem Solving Guide for Mechanics and Thermodynamics. We have a 500-gram chunk of brass at 800 degrees Celsius. We quench it in 2 kilograms of water that starts at 20 degrees Celsius. What's the final equilibrium temperature of the water? The specific heat of brass is 380 joules per kilogram for every degree Celsius. So let's sketch what's going on. We have a brass cylinder. It's 500 grams at 800 degrees Celsius. We have some water, 2 kilograms at 20 degrees Celsius. We stick the brass in the water. They come to equilibrium. What's the final temperature? So we have the specific heat of water, 4,184 joules for 1 kilogram for 1 degree Celsius. Brass is 380 joules for 1 kilogram for 1 degree Celsius. With the equilibrium temperature, the unknown, both of our expressions for Q will have the unknown T final in it. So the magnitude of the energy gained by the water, we can't calculate a number because we don't know T final. But we know it's T final minus 20 degrees. The change in temperature of the water, whatever T final is, it starts at 20, so it's T final minus 20. So there's an expression for the Q gained by the water. Now we need an expression for the Q lost by the brass. It starts out at 800. Its temperature change is 800 degrees Celsius minus T final. Right? If T final ends up at 30 degrees, then we know delta T is 770 degrees. Our equation gives us the correct number for delta T. Both of these have to be positive because we're going to set them equal to each other. If one's positive and one's negative, they can't be equal to each other. So we're setting the magnitudes of the thermal energy transfer equal to each other. So now we just have math to do. So the first thing we're going to do is multiply through these two numbers. We're going to multiply through these two numbers like that. So for water, that's what we started with. Now we're going to multiply it through. Then we're going to have two numbers. We have a number with a TF in it, and then we have some number of joules. So 2 times 41,834 times 20 degrees Celsius, that is minus 167,360 joules. And there's our variable, that's 2 times that. For brass, it's this. We're going to multiply through the half times the 380, which is 190. So that becomes this. And now we can set them equal. There's a lot of math here. So we have this equal to this. We can collect the T final terms and put them on the same side. And we can collect the two energies and put them on the same side. Now we just have to divide by 8,558 joules per Celsius to get T final, and we get 37.5 degrees, 37.3 degrees for T final. That sounds about right, but we did a lot of math, and whenever we do a lot of math, I have a big propensity to make a mistake, so I like to check the answer. So what I'm going to do is I'm going to calculate how much energy the water lost. If the equilibrium temperature is indeed 37.3, the temperature of the water went up by 17.3, started out at 20. If it ends up at 37.3, delta T for the water is, if it ends up at 37.3, delta T for the water is 17.3, and delta T for the brass is 762.7 because this started at 800. So I'm just going to calculate the Q's. 2 kilograms of water, there's the specific heat, there's the delta T. It's 144,900 joules gained by the water. The thermal energy lost by the brass, half a kilogram, 380 joules per kilogram per degree Celsius. There's the delta T, and you punch in the numbers, and you get 144,900. Bingo. Gotta be right. That's problem 1.